Right now, in a laboratory in Beijing, a team of scientists has built a refrigerator with no compressor, no refrigerant gas, and no moving parts. It runs on magnets. And if they can scale it, the machine sitting in your kitchen right now, the one humming in the background as you read this, is built on technology from the 1800s that might finally be ready to die. Think about that for a second. The refrigerator is one of the most common objects on Earth. There are roughly 1.5 billion of them in homes around the world, and almost every single one of them works the same way. The same basic principle, the same compressor and gas system that engineers figured out in the 19th century and never really changed. Not because it's perfect, because nothing better ever came along. Until now, something might have. The team at the Institute of Physics, part of the Chinese Academy of Sciences in Beijing, published a paper in the journal The Innovation in May 2024. The lead researchers were Yuan Lin, Jing Wang, and Bin Shen. What they described was a device that moves heat without any fluid, without any gas, and without any compressor at all. Just magnetic material, a strong magnet, and a clever layered structure they call a hybrid magnetic regenerator. Here is the thing. This is not a product. It is not sitting on a shelf at your local electronics store. The researchers themselves call it a conceptual device. But what they have shown in that laboratory changes the core argument that has kept magnetic refrigeration stuck at the prototype stage for nearly 50 years. And that is a much bigger deal than it sounds. By the end of this video, you will understand exactly why your refrigerator works the way it does, why it has a serious problem that almost nobody talks about, and why a magnet in a Beijing lab might be the first real answer to that problem in a century. To understand why this matters, you have to start with what is actually happening inside your refrigerator right now. Open the back panel or look at the bottom, and you will find a compressor. It is a small motor, usually black, usually warm to the touch. It hums. Sometimes it rattles. It is the reason your fridge makes that sound late at night when the house is quiet and you are trying to sleep. That compressor is the heart of a system called vapor compression refrigeration. And here is the basic idea. Inside your fridge, there is a sealed loop of refrigerant gas. The compressor squeezes that gas, which makes it hot. The hot gas travels through coils at the back of the fridge, releases its heat into your kitchen, and then cools down and turns into a liquid. That liquid then flows into the inside of the fridge, where it is allowed to expand and evaporate. When it evaporates, it absorbs heat from the air around it, which is exactly what makes the inside of the fridge cold. Then the gas travels back to the compressor, gets squeezed again, and the whole loop repeats, over and over, hundreds of times a day. It is elegant in its own way, simple, reliable, and cheap to manufacture. The Rocky Mountain Institute has documented that this technology has dominated the cooling market for nearly a century, not just in your kitchen fridge, in the freezer section at your grocery store, in the air conditioning unit on your roof, in the refrigerated truck that brought your food to the store, in the pharmacy cooler keeping vaccines at the right temperature, in the walk-in freezer at your favorite restaurant, in the server rooms that keep the internet running, in the battery cooling systems inside electric vehicles. Vapor compression refrigeration is everywhere. It is one of the most widely deployed technologies in human history, and it has two serious problems. The first problem is mechanical. The compressor has moving parts. Moving parts wear out. That is why refrigerators break. That is why air conditioning units need servicing. That is why the cooling system in your car eventually fails. Every time that compressor cycles on and off, it is a little closer to the end of its life. And when it fails, the repair is almost always expensive. The second problem is much bigger. The refrigerant gas inside that sealed loop is not benign. One of the most common refrigerants used today is called R134A. According to the Rocky Mountain Institute, R134A has a global warming potential approximately 1,430 times that of carbon dioxide. Not 14 times, not 140 times, 1,430 times. That means a small leak, the kind that happens when a system ages or gets damaged, releases the equivalent of thousands of pounds of carbon dioxide into the atmosphere from a single unit. Multiply that by 1.5 billion home refrigerators. Add the commercial units, add the car air conditioners, add the industrial freezers, and you start to see why the cooling industry has a climate problem that most people have never heard of. Because the refrigerant is invisible, it leaks quietly, and nobody talks about it at the dinner table. So the motivation for finding something better is real. It is not a science experiment for its own sake. The world has 1.5 billion reasons to find a different way to move heat. The question is, what does that different way look like? Here's where it gets uncomfortable. The answer has been sitting in physics textbooks since 1881. In 1881, a scientist named Emil Warburg noticed something strange about certain metals. When you put them inside a magnetic field, they get warm. When you take them out of the magnetic field, they get cold. Not dramatically cold. Not cold enough to freeze your lunch, but measurably, reproducibly cold. He called it the magnetocaloric effect. Magneto for magnetism. Caloric for heat. The material heats up in the field and cools down when the field is removed. Think about it this way. Have you ever stretched a rubber band and held it against your lip? It gets warm. Now let it relax and hold it against your lip again. It gets cool. The rubber band is storing and releasing energy through its physical structure. Magnetic materials do something similar, but through their atomic structure. When a magnetic field is applied, the tiny magnetic moments inside the material line up in an orderly way. Ordering them releases energy as heat. When the field is removed, they go back to being disordered. Returning to disorder absorbs energy, pulling heat from the surroundings. That is the magnetocaloric effect. No gas, no compressor, just a material responding to a magnetic field. Warburg knew this in 1881. Scientists studied it for decades. But for most of that time, the effect was only strong enough at extremely low temperatures, near absolute zero. That made it useful for specialized physics research, but useless for your kitchen. Then in 1976, a physicist named G.V. Brown changed the picture. Brown built the first magnetic refrigerator that worked at room temperature. He used gadolinium, a rare earth metal, as his magnetocaloric material. Gadolinium has a property that makes it particularly useful. Its magnetocaloric effect is strongest right around room temperature, which is exactly where a practical refrigerator needs to operate. Brown's device worked. It moved heat. It cooled things down. It did not need refrigerant gas. It did not need a compressor. It should have been a revolution. It was not. Brown's device and every magnetic refrigerator built in the decades after it had a problem. A specific, stubborn, technical problem. And that problem is what the Beijing team just figured out how to solve. To understand the problem, you need to understand how a magnetic refrigerator actually moves heat from one place to another. The magnetocaloric material gets warm when the magnet is applied. That warmth has to go somewhere. In vapor compression refrigeration, the refrigerant gas carries the heat through the loop and dumps it outside. In a magnetic refrigerator, the traditional approach was to use a fluid, usually water, pumped through the system. The fluid would flow over the magnetocaloric material when it was warm, carry that heat away, dump it outside, then flow back when the material was cooled to absorb the cold. Back and forth, warm phase, cool phase, the fluid as the messenger. Here's the thing, fluid is slow. Fluid has what engineers call thermal mass, meaning it takes time to heat up and time to cool down. And when you are trying to run a magnetic refrigerator efficiently, that slowness kills you. The system can only cycle as fast as the fluid can move heat. Faster cycling means more heat moved per second, which means better cooling. But the fluid cannot keep up. The faster you try to run it, the more cooling energy you waste, because the fluid is always slightly out of sync with the magnetic cycles. You are always leaving some performance on the table. For nearly 50 years, that fluid bottleneck was the ceiling that kept magnetic refrigeration from competing with vapor compression systems. Researchers built better magnetic materials. They designed stronger magnets. They refined the geometry of their regenerators. But the fluid was always there, acting as a speed limit on the whole system. The team at the Chinese Academy of Sciences asked one question: what if there was no fluid? What if you could move heat directly from one solid to another with no liquid in between? The idea sounds simple. The execution was not. When two solids are in contact, heat moves between them through what is called thermal conduction. But solid-to-solid contact, in practice, is imperfect. There are tiny gaps, there are surface irregularities. The contact area is never as good as it looks. And the result is that solid-to-solid heat transfer has traditionally been seen as too slow and too lossy for this kind of application. That is why fluid was used in the first place. Fluid fills gaps. Fluid conforms to surfaces. Fluid is a better thermal conductor per unit of contact area. The Beijing team's insight was not to ignore that problem. It was to engineer around it. They built what they call a hybrid magnetic regenerator. The idea is to take the magnetocaloric material and layer it directly against a material that has extremely high thermal conductivity, not just touching it, bonded to it, integrated with it. The highly conductive solid acts as an express lane for heat. When the magnetocaloric material heats up under the magnetic field, the heat moves instantly into the conductive layer and out of the system. When the field is removed and the material cools, it draws heat in through that same conductive layer from the cold side. No fluid, no pump, no thermal lag. Just solid material against solid material, with heat moving at the speed that the materials allow. And because there is no fluid acting as a speed limit, the system can cycle much faster. More cycles per second means more heat moved per second. The researchers showed that removing the fluid bottleneck allowed them to run the system at frequencies that fluid-based designs simply cannot reach. The cooling power goes up, the efficiency improves, and the whole device becomes simpler. Because you have removed the fluid loop, the pump, and all the engineering complexity that comes with managing a moving liquid inside a precision system. The paper was published in the Invention in May 2024. It was followed by a second paper in PNAS, the Proceedings of the National Academy of Sciences, which took the idea further. That second paper showed something that goes beyond refrigeration entirely. It showed that solid-to-solid heat transfer in this kind of system can be targeted, precisely targeted. Not just moving heat from one side of a box to the other, but directing heat away from a very specific point, with a level of control that the researchers described as acting like a heat scalpel. Think about what that means in practice. Right now, one of the most difficult engineering problems in the entire electronics industry is heat. Not generating it, managing it. When a processor runs at full speed, it generates enormous amounts of heat in a tiny area. The faster the processor, the more heat per square millimeter. Modern chips are so dense that cooling them is one of the primary limits on how fast they can run. The cooling systems inside high-performance computers are elaborate, expensive, and often the first thing to fail. Data centers spend enormous amounts of money and energy just keeping their servers cool. Heat is the enemy of every electronic device you own. If you could direct a heat scalpel at a specific hotspot on a chip, pull the heat out of exactly that point, and move it away without touching anything around it, you would have a tool that the electronics industry does not currently have. Not a fan blowing air over a surface, not a heatsink conducting warmth away passively. An active, targeted, solid-state cooling system that addresses heat exactly where it is worst. The same logic applies to electric vehicle batteries. An EV battery pack generates heat unevenly. Some cells run hotter than others. Uneven heat is the enemy of battery life. If some cells get too hot while others stay cool, the pack degrades faster, charges slower, and loses range sooner. Current battery thermal management systems use liquid cooling loops, which are heavy, complex, and subject to leaks. A solid-state system that could target heat at specific cells, pulling it away from the hottest points without any fluid, would be a significant step forward for battery longevity and charging speed. Here's where it gets uncomfortable. The technology that could do all of this is still sitting in a laboratory in Beijing. It is not in your phone, it is not in your car, it is not in your refrigerator. The researchers themselves are explicit about this. The device described in their papers is a conceptual device. Those are their words, not a critic's characterization. A proof of concept, a demonstration that the physics works the way they predicted. Not a product, not a prototype ready for manufacturing. A scientific result that shows the door is open. That distinction matters. Because the history of magnetocaloric refrigeration is full of moments where someone said, "We solved the problem," and then the technology sat for another decade. G.V. Brown built a working room temperature magnetic refrigerator in 1976. That was 49 years ago. The technology is still not in your kitchen. So when a new paper comes out showing a genuine advance, the right response is not to assume your fridge is obsolete by next Tuesday. The right response is to understand what actually changed, why it matters, and what still needs to happen before it becomes real. What actually changed is the removal of the fluid bottleneck. That is not a small thing. That specific problem, fluid acting as a speed limit on heat transfer, was the core reason magnetic refrigeration kept losing efficiency comparisons to vapor compression systems. Every time a research team built a magnetic refrigerator and measured its coefficient of performance, which is the technical term for how much cooling you get per unit of energy you put in, the fluid was dragging the number down. Solve the fluid problem, and you remove the single biggest obstacle to competitiveness. What still needs to happen is substantial. The magnetocaloric materials that work best, like gadolinium and its alloys, are rare earth metals. Rare earth metals are not cheap. They are not easy to mine or process. They are not available in the quantities you would need to put a magnetic refrigerator in every home on Earth. Gadolinium costs significantly more per kilogram than the refrigerant gases it would replace. And the strong compact magnets needed to apply and remove the magnetic field efficiently are also expensive. The current cost of a solid-state magnetic cooling system is much higher than the cost of a conventional compressor-based system that does the same job. That cost gap is not impossible to close. It has been closed before in other technologies. Solar panels in 2000 cost roughly $4.50 per watt. By 2023, the average cost was around 20 cents per watt. Lithium-ion batteries in 2010 cost around $1,200 per kilowatt hour. By 2023, that number had dropped below $140. Cost curves in manufacturing can move fast when the technology is proven and the demand is there. But those transitions took decades and billions of dollars in investment. Magnetic refrigeration would need the same kind of sustained push. There is also the question of efficiency. Vapor compression refrigeration, despite its age and its environmental problems, is genuinely efficient at what it does. Modern refrigerators use a fraction of the electricity that the same size refrigerator used in 1980. The technology has been optimized for a century. A new approach does not just need to be cleaner. It needs to be at least as efficient, ideally more so, at a cost that the market will accept. The solid-state magnetic approach has theoretical advantages, particularly at smaller scales and in targeted cooling applications. But converting theoretical advantage into measured real-world efficiency at a competitive price is a long road. None of that diminishes what the Beijing team did. It is a genuine scientific step forward on a problem that has been stuck for 50 years. But the honest version of this story includes both the breakthrough and the distance still to travel. So what does this mean for you right now? In the short term, probably nothing visible. Your refrigerator will keep humming. The compressor will keep cycling. The R134A inside that sealed loop will keep doing its job and eventually leaking. The world will keep running on vapor compression refrigeration for years, possibly decades, while researchers work on closing the cost and efficiency gaps in solid-state alternatives. But here is the part that makes this story worth paying attention to. The problems with vapor compression refrigeration are not getting smaller. They are getting bigger. The world is getting warmer, which means more air conditioning demand. More air conditioning demand means more refrigerant in more systems. More refrigerant means more potential for leaks and more climate impact. At the same time, the electronics industry is hitting hard limits on chip performance because of heat. EV batteries are limited by thermal management. Data centers are consuming more power for cooling than for computation in some cases. The demand for a better answer to the heat problem is growing faster than the current technology can keep up. The Chinese Academy of Sciences team did not solve all of those problems, but they removed a 50-year-old roadblock in the path towards solving them. That is how most real technological progress works, not one announcement that changes everything overnight. A series of specific, unglamorous technical problems that get solved one at a time in laboratories that most people will never visit, by researchers whose names most people will never know. Yuan Lin, Jing Wang, and Ben Shen published their paper in May 2024. It did not make the front page of any newspaper. There was no product launch. There was no keynote presentation in a glass auditorium. There was a paper in a journal, a follow-up in PNAS, and a result that the people who work on this problem will be building on for years. The effect was discovered in 1881. The first room temperature device was built in 1976. The fluid bottleneck was the ceiling for 48 years. Now the ceiling has moved. What gets built under the new ceiling is the part of the story that has not been written yet. But think about where it could go. A refrigerator with no compressor is a refrigerator that does not hum. It does not vibrate. It does not have a motor that wears out after 10 years. It does not have a sealed loop of gas that can leak and warm the atmosphere. A solid-state magnetic refrigerator, if the material's cost comes down and the efficiency matches what the physics suggests is possible, would be quieter, longer-lasting, and dramatically cleaner than anything in your kitchen right now. A targeted solid-state cooling system for electronics means processors that run faster because heat is no longer the limiting factor. It means EV batteries that last longer because individual cells can be kept at their optimal temperature without a heavy liquid cooling loop. It means data centers that use less electricity on cooling and more on computation. The scale of what changes if this technology matures is not small. Cooling is one of the most energy-intensive activities on Earth. The International Energy Agency estimates that space cooling alone accounts for roughly 10% of global electricity consumption. Add refrigeration, electronics cooling, and industrial processes, and you are talking about a very large fraction of the world's energy budget being spent on moving heat from one place to another. A fundamentally better way to do that does not just affect one industry. It touches almost every part of modern life. That is the context for a paper published in a journal most people have never heard of, by researchers at an institute most people could not locate on a map. Here is the other part of this story that is worth sitting with. The magnetocaloric effect has been known since 1881. That is 143 years of knowing that certain materials heat up in a magnetic field and cool when the field is removed. For most of that time, the effect was interesting but not useful at room temperature. Then G.V. Brown made it useful at room temperature in 1976. That was a breakthrough, but the fluid problem kept it from competing with the technology it was supposed to replace. For nearly half a century, a promising idea sat in a holding pattern because of one specific engineering bottleneck. This is how technology actually works, not the version where a genius has a single insight and the world changes the next day. The version where a phenomenon is discovered, then a prototype is built, then a bottleneck is identified, then the bottleneck resists solutions for decades, then someone from a different angle figures out how to route around it, and then the whole thing starts moving again. The timeline is long, the steps are small, the people doing the work are mostly invisible to the public. The Chinese Academy of Sciences team routed around a 50-year bottleneck. That is the story. Not your fridge is obsolete. Not China solved cooling. A specific, measurable, documented scientific step forward on a problem that has been stuck since before most of the people watching this were born. Whether it becomes a product depends on things that have nothing to do with the physics. It depends on whether the cost of rare earth materials comes down. It depends on whether manufacturers see a market large enough to justify the investment in new production lines. It depends on whether regulations tighten on high global warming potential refrigerants fast enough to create pressure for alternatives. It depends on whether a company somewhere decides this is worth betting on and puts serious money into scaling it up. None of those things are guaranteed, but all of them are more possible today than they were before May 2024. The last time a fundamental cooling technology got displaced, it happened slowly and then all at once. Ice harvesting, the practice of cutting ice from frozen lakes and shipping it to cities, was a major industry in the 19th century. Hundreds of thousands of workers, complex logistics, a supply chain that fed restaurants, hospitals, and homes across the United States. Then mechanical refrigeration arrived. Not overnight, not in a single announcement, gradually then completely. By the 1930s, the ice harvesting industry was gone. The people cutting ice in 1890 were not worried. The technology worked, the business was profitable, the demand was there. They had no reason to think the whole thing would be gone in 40 years. The compressor in your refrigerator has been running the same basic play since the 1920s. It has been refined, miniaturized, and made more efficient, but the principle is unchanged. A gas gets compressed, releases heat, expands, absorbs heat, repeat. 100 years of iteration on the same idea. In a laboratory in Beijing, a team of researchers is working on what comes after that idea. They are not there yet. but they found a way past a wall that stopped everyone else for 50 years. That is not nothing. That is exactly how the next thing starts. If this video gave you something new to think about, hit the like button and subscribe so you don't miss what's coming next. Turn on notifications too, because the next story out of China makes this look like just the beginning. Now I want to hear from you. If a refrigerator came out tomorrow with no compressor, no refrigerant, and a 30-year lifespan, would you pay more for it, or would you stick with the cheaper option you already know? Drop your answer in the comments below. I read every single one. The refrigerant problem is worth spending one more minute on, because it is the part of this story that tends to get buried under the engineering details. When researchers talk about R134A having a global warming potential 1,430 times that of carbon dioxide, that number can feel abstract. So here is a concrete version of it. A standard home refrigerator contains roughly 50 to 200 grams of refrigerant. A car air conditioning system holds somewhere between 400 and 900 grams. A commercial walk-in freezer can hold several kilograms. Now think about what happens when those systems age. Seals degrade, fittings loosen. A slow leak over 3 or 4 years might release half the refrigerant charge into the atmosphere without anyone noticing, because the gas is invisible, odorless, and silent. The system still cools, just not quite as well as it used to. Most people assume the fridge is getting old. They do not think about what left through the seals. Now multiply that across every aging refrigerator, every car with a slow AC leak, every commercial freezer running past its service interval. The cumulative effect is significant. The cooling industry accounts for a meaningful share of global greenhouse gas emissions, not just from the electricity it consumes, but from the refrigerants themselves escaping into the air. A solid-state system with no refrigerant does not just save energy, it removes that leak pathway entirely. There is nothing to escape because there is no gas in the loop. That is a different kind of environmental argument than the one people usually make about new technology. It is not just about efficiency. It is about eliminating a failure mode that is built into the current design. And that failure mode is not going away on its own. The industry has been transitioning to lower global warming potential refrigerants for years. R134A is being phased down in many applications in favor of alternatives like R32 and R1234YF. Those newer refrigerants are better. R1234YF has a global warming potential of about 4, compared to R134A's 1,430. That is a real improvement, but it is still a gas. It still leaks. It still requires a compressor and a sealed loop and all the mechanical complexity that comes with it. The transition to lower GWP refrigerants is a step in the right direction, but it does not change the fundamental architecture of the system. Magnetic refrigeration, if it gets there, does not take a step in the right direction. It steps off the road entirely and builds a new one. That is the ambition. The gap between ambition and reality is still wide, but the gap is narrower than it was in May 2024, and narrower than it was when G.V. Brown switched off his gadolinium prototype in 1976 and wrote up his results. There is one more dimension to this story that has not come up yet, and it is the one that tends to surprise people the most. The Chinese Academy of Sciences is not a startup. It is not a venture-backed lab chasing a product launch. It is one of the largest and most systematically funded research institutions in the world. It has roughly 100 institutes across China, covering everything from mathematics to oceanography to materials science. Its annual budget runs into the tens of billions of yuan. It employs tens of thousands of researchers, and it operates on a time horizon that most private companies cannot afford to think about. When a team at the Institute of Physics publishes a paper on solid-state magnetic refrigeration, it is not a press release. It is a result from an institution that has been building toward it, funding it, and staffing it for years. The follow-up paper in PNAS did not appear because someone got lucky. It appeared because the institution had the resources and the continuity to keep pushing after the first result. That matters for how you interpret what comes next. The Beijing team did not publish their paper and then move on to something else. They are still working on it. The follow-up in PNAS is evidence of that. There are almost certainly more results in the pipeline. The question is not whether the research continues. The question is how fast the gap between laboratory result and manufacturable product can be closed, and whether the investment required to close it will materialize. China has a track record of making that kind of investment in areas it decides are strategically important. Solar panels, lithium-ion batteries, high-speed rail, electric vehicles. In each of those cases, the technology existed elsewhere, sometimes for decades, before Chinese manufacturing investment drove costs down to the point where the rest of the world had to respond. Whether magnetic refrigeration becomes the next item on that list is not certain, but the institutional machinery to make it happen is already in place. The rest of the world is paying very close attention. Research groups in the United States, Europe, and Japan have been working on magnetocaloric refrigeration for decades. The Technical University of Denmark has a long-running program on magnetic refrigeration. The Lawrence Berkeley National Laboratory in California has published work on magnetocaloric materials and systems. The European Commission has funded projects through its Horizon research programs aimed at bringing magnetic cooling closer to commercial viability. This is not a field that only China is working on, but the specific advance in the May 2024 paper, the fully solid-state heat transfer with no fluid, is a result that came out of Beijing. And in the competitive landscape of materials science and cooling technology research, being first to publish a working demonstration of a key concept matters. Other teams will now try to replicate it, improve on it, and build on it. That is how science works. The Beijing paper becomes a reference point. Every future paper on solid-to-solid magnetocaloric heat transfer will cite it. That is a quiet kind of influence. Not a product launch, not a factory opening, a citation in a journal that other researchers around the world will follow. Quiet is often how the biggest changes start. Think about the transistor. The first one was demonstrated at Bell Labs in December 1947. It was a small, fragile device made of germanium and gold foil. Nobody watching the demonstration thought they were watching the birth of the smartphone. They thought they were watching an interesting physics result. The transistor sat in research papers and specialized electronics for years before it found its way into commercial products. Then it found its way into everything. The gap between the Bell Labs demonstration and the device in your pocket was about 70 years of incremental work by thousands of researchers and engineers whose names you will never know. The magnetocaloric effect has been in research papers for 143 years. The first room temperature device was built 49 years ago. The fluid bottleneck held the technology back for most of that time. Now the bottleneck has been addressed in a peer-reviewed paper by a named team at a well-funded institution with a follow-up result already published. Where does it go from here? The most likely near-term application is not your kitchen refrigerator. The economics of replacing a $500 home appliance with a new technology are brutal. The cost has to come down dramatically before that makes sense for a mass market. The near-term applications are the ones where the current cooling technology is most inadequate, where the cost of failure is highest, and where the benefits of a solid-state system are most immediate. Electronics cooling is the obvious first candidate. The semiconductor industry is already spending enormous resources on thermal management. A chip that runs 10 degrees cooler can run faster, last longer, and consume less power. If a solid-state magnetocaloric cooler can target heat at a specific point on a chip with the precision the PNAS paper suggests, the value proposition for a high-performance computing application is strong even at a higher cost per unit. The market does not need to be millions of units for the economics to work. It needs to be the right units in the right applications, where performance matters more than price. EV battery thermal management is the second candidate. The battery pack is one of the most expensive components in an electric vehicle. Extending its life by even 20% has significant economic value. If solid-state cooling can keep individual cells at a more uniform temperature, reducing the stress that comes from hotspots, the payback calculation changes. And unlike a home refrigerator, an EV battery cooling system is a component that automotive engineers are actively redesigning right now because the current liquid-based systems add weight, complexity, and failure risk that the industry is motivated to reduce. Data center cooling is the third. The numbers there are staggering. A single large hyperscale data center can consume 100 megawatts of power or more. A significant fraction of that goes to cooling. Companies like Google, Microsoft, and Amazon are spending billions of dollars trying to solve the heat problem in their server farms. They are experimenting with liquid cooling, immersion cooling, and novel heat exchanger designs. A solid-state targeted cooling system that could address heat at the chip level, inside the server without any fluid in the loop, would be worth an enormous amount of money to those companies, even at a significant cost premium over conventional cooling. Those three markets, high-performance electronics, EV batteries, and data centers, are where the technology is most likely to prove itself commercially before it ever touches your kitchen. And if it proves itself there, the manufacturing scale and the cost reduction that follows could eventually make it viable for consumer appliances. That is the realistic path, not a straight line from laboratory to living room. A diagonal route through the highest value applications first, with the cost curve bending down as volume increases, until one day the economics work for the mass market too. It is the same path that LED lighting took. For years, LEDs were expensive and used only in specialized applications where their long life and low heat output justified the cost. Indicator lights, traffic signals, exit signs. Then the cost came down, the efficiency went up, and suddenly LEDs were in every home fixture on the street. The incandescent bulb, which had been the dominant lighting technology for over a century, went from universal to obsolete in about 15 years once the cost curve broke. The compressor in your refrigerator has had a longer run than the incandescent bulb, but the physics that could replace it has been waiting in the wings since 1881. The team at the Chinese Academy of Sciences just gave it a meaningful push toward the stage. Whether it arrives in your kitchen in 10 years or 30 years, or not at all in your lifetime, depends on decisions being made right now in boardrooms and government ministries and university funding committees that have nothing to do with the elegance of the underlying science. But the science is real. The result is published. The bottleneck is gone. And somewhere in Beijing, Yuan Lin, Jing Wang, Baiyan Shen, and their colleagues are already working on what comes next.